Yeah. Okay, so we are where we left last class. The same diagram remains. Just to make a recap, this is the equation that we used. This is the condition that we used, that the solid is always pure. And this expression, and this is how the liquidas of A intersect. Below this, of course, there is no melt, and this is called the solidus. And this temperature at which this occurs is called the temperature of the eutectic, and this is what is called the composition of the eutectic. This diagram is temperature, as you can see here, and on this side this is a composition diagram. It's a composition diagram where there, for a binary, A is 1.0 or 100 weight percent, and B is here B is 1, XB is 1, or B is 100 weight percent. So now we will start with trying to understand how crystallization proceeds. Some of you may already know, but I think it's best to recap on that, and then we go to melting and see what are the complications. Okay, so So, before we start, this is a binary. A is pure solid, remember, pure solid. B is pure solid. A plus B is a mixture of pure A mineral and pure B mineral. So here it's pure A mineral, pure B mineral, plus liquid. Here it's plus liquid, and here it's pure A mineral, pure B mineral, and with no liquid. And here, above the liquidus, you have no solids. It's all liquid. Yeah, so far so good. Now, we look at a few things. Let's take a melt composition here. Let this be a melt composition. We call it L0, melt composition. Now, when I say melt composition, what does it mean? It means that if I take this line and take this line, and I join this line here, so you have this part and this part. This is the weight percent A or XA in brief, and this one is XP. Now, so roughly, you see this is 50%, so let's say this is 75%, or 0.5, this is 0.75, and this is 0.25. Let's say it's like this. Now you see, if I take this point and project it vertically down, I will reach this point. What is this point? XA is equal to 0.25 and XA is 0.75 and XB is equal to 0.25, which is this point, composition of this point. Now, important, and this is very important. What does XA? What is this XA? There is no crystal above this, yet I call XA. There is no crystal above this, yet I call XB. What is this XA and XB? Now, this is very, very important to understand. These are milk molecules. Have you understood? Milk molecules in solid solution. Just like I've taught you before, this is milk molecules in solid solution. This is very, very important to understand it. This XA does not mean that it has 7.75% A and this is 25% B mineral. No. The point is, a melt here, XA is 0.75. That means a melt molecule or a melt component or a melt phase component is A, whose composition has a particular composition. That is A. And here XB means that the melt has this component B. It's not a mineral, it's a component B. So essentially the melt is a solid, is a liquid solution. Melt A is then a liquid solution of A and B, where A and B are in the proportion 0.75 to 0.25. There is no solid A, there is no solid B. So, in this range, your melt is a melt solution. It's a chemical compound of whose composition can be bracketed by A and B. And A is their 75%, B is their 25%. You might say, why is repeating? When we go further, you will see dangerous inferences, tremendous inferences we will get from this. This is very important to understand. We have molecules of A, molecules of milk molecules in solid solution, inseparable. They form a chemically homogeneous liquid. You can't separate A and B. They form part of a liquid solution. Now, during crystallization, we are now learning about crystallization. During crystallization, the temperature, of course, decreases. And therefore, the melt, the coordinates of the melt move along this line and it reaches here. Have you understood? So, when it reaches here, what it reaches here? The temperature of the melt. Mark the words. The temperature of the melt here coincides with the temperature of the liquidus. Have you understood? With the liquidus curve. Where does it intersect? At this temperature. So this is, say, T1. This is T1, where the melt is now coinciding with the liquidus of A. So here A and the liquid are in equilibrium. So if A and liquid are in equilibrium, then where is A now? Now at this temperature T1, the first solid that crystallizes is S1 and this is L. This is L0 and here the first solid comes in. The first embryo of the crystal of A has started to form, which is S0. What is the composition of S0? The composition of S0 is A. The composition of S0 is A. Have you understood? What is the composition of L0? Almost the same as before. But since from the melt you are precipitating pure A, So the melt composition needs to move in this direction. But, and also down temperature because you're cooling. But the melt composition, therefore, what it does is, the melt composition moves along this line. Neither straight away, nor down temperature, but it follows the liquidus. It follows the liquidus. Have you understood? So, L0 now becomes L1. Why L1? Because some of this solid A has been separated out from the melt L0. So the melt composition will move away from A. So it will become, the melt will become richer in B because A is being crystallized continuously, but is in contact with the melt. A is in contact with the melt. But only thing, A is now a crystal, your solid now is solid now at L0, solid was S0, so at this temperature now, at a lower temperature, this is a temperature T2, you will have solid S1. Solid is now S1, not S0. Which is in equilibrium with the liquid L1. Now you can draw a line here and you see your liquid composition has changed, maybe from 0.75 to 0.70, and this has moved to 0.30. So what has happened? The liquid composition has changed. It has become poorer in A component. Why? Because A crystals have been taken out. Now we ask ourselves, what is the difference between S0 and S1? What is the difference? Solid S0 and solid S1, what is the difference? Both have the same composition A. So what is the difference? Now is the catch, and this is very, very important. The composition of S0 and S1 are the same. Yes, correct. The composition of is same. But say I take this line which is joining S1 and L1 and I draw this original line, this point. What is this point? Let's say this is M and this is M. This is M, that means, let's say we write this as L0, just to keep it as L0. So, S1 L0, this is equal to M, and L1 L0, this is equal to M. Why am I drawing this? Question. You see, it is a closed system. The magma crystallization, let's assume it's a closed system. So whatever you do with the magma and the crystal, the composition of the system is not going to change. So the composition remains the same. So all along, the L0 composition has remained same. Now what is M and N? What is M and N? N is the proportion, here you see, M if I take this proportion of L1, what is the proportion of L1? The proportion of L1 is M. And the proportion of S1 is M. The proportion of L1 is M. And the proportion of S1, proportion of not S1, proportion of A is M. Have you understood? Because the proportion of the solid and liquid will move such that the initial composition is not changed. So there is a mass balance composition. Have you understood? The total composition has to be conserved. And this will control the proportion of the liquid and the solid. So the proportion of liquid is M at this point, and the proportion of solid A is N is this point. So now you can see, so here the solid S1, the composition is A100. Have you understood? The composition of solid is equal to A. That's right. Composition of solid is equal to A. Proportion of solid is equal to A. Proportion of solid is equal to M divided by M plus N. Or the fraction of melt is equal to N divided by M plus N. So what is the difference between S0 and S1? Both have the same composition. Both S1 and S0 has the same composition of that A. But the proportion of the solid in S1 is more than S0. Both S0 and S1 has the composition of A, yes. But the amount of A in the solid is more. So the difference between S0 and S1 is that in S1 there is more of pure A than S0. Now let's say we go back from L1 to L0 again. We go back to L0. So what will happen, you see? This N, as this point moves here, the N will become 0. So the fraction of milk will become 0. So the fraction of solid will become, the fraction of solid will become 0. N will become 0. Oh, the fraction of milk, sorry. The fraction of milk is this, I'm sorry. The proportion of solid is equal to N divided by M plus N, and the proportion of the melt is M divided by M plus N, right? So, when we go back to L0, you can see the proportion of the solid will become 0 because N will become 0. And the proportion of melt M will become equal to 1. Have you understood? The proportion of melt will become equal to 1. So, that is a very important thing. First is, as you change in this type of crystallization, which is called equilibrium crystallization, the composition of the solid changes. We will see more, but for this point, the composition of the solid initially changes. Only thing, the composition is the same, but the proportion of the solid of pure A becomes more, and the liquid becomes more B-rich as more and more A crystallizes as temperature goes down. So let's say we take a point here. Say, let's say this is L2, so you will have S2, and here you see is the same line. Here you see is the same line now, initial, this is L0. So now you can see, this is M, and this is M. So you see, the length of M is not changing, but the length of N is increasing. If the length of N increases, that means the proportion of the solid increases. So here, your S2 also has the same composition as S1 and S0, but in S2, the proportion of the solid is more. Solid A is more, given by M divided by M. That is how crystallization will continue. Till, and you see your liquid composition now, here, you see your liquid composition at L2, now it has become maybe 0.30 or something. XA will become 0.30 and this has become 0.70. So you see the composition of the melt is progressively becoming impoverished in A and becoming richer in B. The composition of the melt is becoming richer in B because A is being extracted, crystallized as solid, and A component is decreasing. At the same time, the fraction of liquid, M divided by M plus N, you see this is small but this is becoming larger, so the fraction of melt is decreasing because more and more solid is increasing, or the fraction of solid is increasing. So remember, this is important, and this will happen till we reach this point. Till we reach this point and the liquid reaches this point. Let's say this is L3 and this is S3 and the temperature is T3. Now, at L3, XB now has become 0.75 and XA now has become 0.25. By the time the liquid composition reaches the eutectic, A and B components in the liquid are in the proportion 0.75, 0.75B and XA is 0.25. That is the composition or proportion of A and B in the chemically homogeneous melt. But the solid composition is still here. The time when the liquid reaches almost this, your solid composition is still here. The composition is still pure A, but the proportion of N, you can see, has increased further. That means the proportion of the solid has increased even more. Now is the catch. When the liquid composition reaches the eutectic composition, see here, the liquid L3 now has the same composition as the eutectic. Means what? The liquid now has XA 0.25 and XB 0.25. What is this A and B I told you? These are the melt components. Have you understood? These are the melt components. Now at this point, what is an equilibrium? The liquid L3 will be in equilibrium with A and B. These will be the three phases. Liquid L3 of composition XB 0.75, XA 0.25 plus pure A plus pure B. These are the three phases that are in equilibrium. So now what will happen? A and B both will co-precipitate. When I say A and B, I mean pure A and pure B crystals will precipitate from the melt whose composition is XA 0.25, XB 0.75. Think again. There are three things in equilibrium. A liquid L3 with XA equal to 0.25, xb equal to 0.75, it will be in equilibrium with A, where xa is equal to 1.0 and B where xa is equal to 0.0. That means xb is equal to 1.0. This will be the condition. This will be the condition at the eutectic. So what will happen? More A and B, more A and B will precipitate. More A and B will precipitate from the melt. So what will happen? Look at the solid S3. Solid S3 is still now pure A. But when you precipitate pure A and pure B, your solid composition, the solid point which marks the composition of the solid, it will not be able to lie on the vertical axis, yes or no? It will not be able to lie on the vertical axis because B is being added. So what will happen is the solid composition will move inside the binary. Inside the binary. I give you a little time to think about it. So once liquid L3 starts to precipitate, there will be S3, A, more A and new B, all pure, will add to the initial composition S3. So what will happen? This composition S3 will have to move inwards to accommodate more A and new B. So this point cannot stay anymore on the vertical axis, but it has to move along the eutectic. Why eutectic? Because this is the only point in the phase diagram where a melt coexists with two pure solids. So there is no further melt in this composition, in this diagram. No further melt. Melts don't exist below the eutectic temperature. So what will happen if you have to have melt A and B? Then it has to be this point and no other point. So what will happen? Where will be L4? L4 will also be here. We'll have the same composition as L3 because the composition is the same as you can see. But it will precipitate A and B. Now you see, if the liquid has to maintain the same composition, proportion of A and B components, then it has to precipitate A mineral and B mineral in the same proportion to keep the ratio same. Do you understand? Say for example, if in a class there are 20 students, 10 girls and 10 boys. So if 5 girls go out, to keep the ratio same, 5 boys have to go out. So the number of students decrease, but the ratio of the girl and boys don't change. So what will happen here? A and B at the eutectic, A and B means A crystal, pure A crystal and pure B crystal will precipitate from the melt in the proportion of XA and XB. In the proportion XA and XB, so that the composition of the melt will not change, but the proportion of the melt will change. The composition of the melt will not change, but the proportion of the melt will change. That is a very important point. When you move from L3 to L4, the proportion of the melt will change. The composition of the melt will not change. And the solid composition has to move inwards to say L4. Solid composition has to move inwards along the eutectic temperature because below this temperature melts are no more existing. So the the solid composition has no way but to move along this eutectic temperature. So what will happen now? You see what is happening again now. Now you have, this is now your, from this point to this point. Now you see what's happening. This is very important. This is now your M. And this is now your N. What is M? Once again I'm drawing it. L4, this is L0, yes? So, what is at this point? What is M? L4, L0 is equal to M, and L0 eutectic is equal to N. Have you understood? So, now you see here something is interesting is happening, and this is very crucial for you to understand. Take your time. I will give you a little time for you to understand. Okay. Recollecting. I hope you have understood that from crystallization from L3, for which the solid is S3, just before touching this point, your solid is S3 pure. When you reach this point, that you can't change the temperature anymore, because in this diagram, the only point where A, pure B, and liquid are in equilibrium is only at this point. There's no other point where the three phases, pure A, pure B, and liquid are in equilibrium. So now whatever you do, your liquid is not going to move away from that very crucial point called the eutectic. And when the liquid composition has moved here, the composition of XA was 0.275, XB 0.75. That was the composition of the melt. And what did it precipitate? Pure A, XA is equal to 1.0. And pure B, XB is equal to 1.0. Pure A and pure B, it was precipitated. So if the liquid can't change its position, then what is happening from L3 to L4? What is happening is the liquid has A component and B component in a particular proportion. Have you understood? So to keep the composition same from L3 to L4, A and B components will be precipitated as pure A and pure B solids. Pure A and pure B solids. So S3 composition now has to move to this position, which is, sorry, I have made a mistake. This is S4. So you have here now S4L0 is equal to M, and L0EN, L0E, this is equal to N. So what is happening? This M is now starting to decrease, but this N remains constant. So if M starts to decrease, you can see the fraction of melt decreases, and N now increases, which is the proportion of the solid. But now, what is the composition of the solid? At S4, what is the composition of the solid? You draw a line. Here, A is possibly 90% and B is possibly 10%. So now your solid S4 is no more pure A. It is now 90% A and 10% B. Have you understood? So from S1 to S3, the composition of your solid was pure A. But from S3 to S4, the composition of your solid is no more A100. It is now A90, B10. Why? Because A and B in the proportion, A mineral and B mineral, precipitated in the same proportion as XA and XB in the melt. So if you precipitate the two in the same proportion, the composition does not change, but the total amount of the melt changes. total amount of the melt changes. So when will this stop? When will the crystallization stop? That's the question. It's very simple. When n is equal to 0. When will melt fraction will become 0? That means the whole rock will become solidified? The answer is very simple. When m is equal to 0. When will m become 0? When S4 reaches S5. That S5 and L0 coincide. That is where m will be equal to 0. So, the final solid, and this will be the last melt here, will exhaust. The last melt will exhaust. Because there cannot be any more melt, because the whole melt has solidified. At the eutectic, the melt in the proportion AB at 0.75, 0.25 precipitated A and B in the same proportion as pure solids. But at one point of time, you had to exhaust. I was telling you, if you had in the class 20 boys, and there were 10 girls and 10 boys, so out of the 10 girls, if 2 have to go, then 2 of the boys have to go to keep the composition of the class same. But the class becomes smaller in size. So here it is, exactly the same logic. Exactly the same logic. But if you go on taking away 2 girls and 2 boys in steps, finally you will have no one in the class. That's where your melt composition becomes 0. It's exactly the same situation, eutectic. So when you have S5, your L5 is still here at the eutectic. Still here at eutectic. It has not left eutectic. So now what we see is, when the solid composition moved from S0 to S1 to S2 to S3 to S4 to S5, that means if I draw the line, so this is the line, I hope this pen works, this is the path the solid took. This is the path the solid took. And this is the path which the melt took. There are 2 paths. This is the path along which the melt changed its composition. This is the path along which the solid in equilibrium changed its composition. First the solid. What happened to the liquid overall, you can see. The liquid overall became moved on this side. That means overall it became B-rich. But the moment the liquid reached the eutectic, its composition did not change anymore. I can't show this because the liquid will always remain here. So the liquid composition changed, became B-rich, reached the eutectic. Once the melt reached the eutectic, the composition of the melt could not be changed anymore. Right? And the solid, from S0 to S1 to S2 to S3, it composed of pure A. From S3 to S4 to S5, the solid became B-rich as more and more A and B precipitated. As more and more A and B precipitated. This is the path that was followed by the solids, composed of initially pure A and later A and B, which was precipitated in the same proportion as components A and B in the liquid. Now, before we conclude, it's important now, S5, the last solid, has the same composition as the initial melt. Has to be. Because it's a closed system. Your last solid composition S phi is equal to the composition of the initial melt. What is the composition of the last melt? The last melt was had the composition of the eutectic. Had the composition of the eutectic. The last melt had the composition of the eutectic. And the last solid had the composition of the initial melt. Although the last solid was in equilibrium with this last eutectic melt. That is very crucial. The composition of the last solid is the same as the initial melt. But the last solid was never in equilibrium with the initial melt. It never was. That last solid was in equilibrium with this eutectic composition. That is what it's all about. You have to understand. Now this type of crystallization is called equilibrium crystallization. Equilibrium eutectic crystallization. I have talked here into a binary system. First let me get this clear, and then we will go to quaternary, and we will go to ternary and quaternary systems if time permits. But this is equilibrium eutectic crystallization. Equilibrium crystallization means that the solids is perpetually in equilibrium with the melt. I'm not saying they're physically in contact, but what they are is they are in equilibrium with the melt. Now equilibrium may or may not be achieved, but that's a very more complicated issue. What I am saying is that the crystal solids are in equilibrium with the melt. It would be easier to expect for you that the solid and the liquid are in physical contact. Have you understood? They are in physical contact. So all type of interaction across the crystal melt equilibrium will be maintained. That much looks easier. But it is also possible that materials can remain in equilibrium even though they may not be in a physical contact. Like in virus time, I can still teach, although we are miles apart. But if the virus wasn't there, we would be teaching across very short distances. Yeah? Sure. Remember, physical contact to achieve equilibrium is easier to explain. But maintaining equilibrium with no physical contact is more difficult to explain. But there are hundreds and thousands of examples of rocks which do it. But it depends on temperatures, it depends on fluids, it depends on a lot of things. But not always physical contacts are the most important criteria for equilibrium. No, it is not. But in this case, we assume this. So, finally, I will conclude this by saying the following, that this is the path of the liquid, where the liquid composition constantly changes from L0 to L1 to L2 to L3, where the solid composition has the same composition, only thing, the proportion of the solid, that means N divided by M plus N, that increased. Proportion of the solid increased. At the same time over this interval, the proportion of the liquid decreased. So that the total composition of the solid and liquid is the same as the initial composition of the system, which is L0. Then, after reaching L3, the liquid composition did not change. This cannot be shown on this diagram. But the liquid composition did not change. But the solid composition changed. And the solid proportion of the solid also changed. There are two parts to this curve. Here, if you take this as the dividing line, In this, the composition remained the same, of the solid remained the same, and the proportion of the solid increased. But in this part, the composition of the solid also changed as the proportion of the solid increased. That's a very big difference. And on this side of the liquidus diagram, here the liquid composition changed till L3. After that, the liquid composition remained constant. It didn't change. At the eutectic, it never changed. So like, there's a saying in English that every dog has his day. So the solid changed its composition, did not change its composition during the initial part of the crystallization. The liquid did not change its composition in the later part of crystallization. And remember this is a very important thing, that as you started to crystallize in the eutectic system, this solid composition started to move inwards. When did the crystallization stop? When M should be equal to 0. That's when the fraction of the melt will become 0. Solid composition and L0 will coincide. That's the only point where M is equal to 0. Have you understood? Okay then. I think we stop here. In the next slide, we will talk about the reverse process of melting. And then we will take up on this melting. And then we will take up the binary of solid solutions. And we will take up the crystallization and the melting altogether. Okay? Thank you.